Welcome to the first video of the semester, as well as the first video of our coverage for NMR. Typically, these videos will involve me in front of a very makeshift-looking whiteboard, but for a lot of our discussion of NMR, it makes more sense to have a voiceover with PowerPoint slides. So I know that might be a little bit disconcerting. It's not necessarily something you're super used to for organic chemistry, but rest assured it's just for this first unit of the class where we'll be using this modality for the most part. So let's go ahead and get started. So we could think about a complex molecule like mitotoxin. Its structure is shown here, and I'm showing you its LD50. This is the lethal dose at which 50% of organisms in a study are killed. So this number means that 50 nanograms, a tiny amount of mitotoxin per kilogram of an animal, will kill that animal 50% of the time. Another way to think about this is that 1 gram of mitotoxin will kill about 1 billion mice. So this is an extraordinarily toxic compound. But one of the things you might be wondering as you frantically try to draw this, or hopefully you're not, is how do we know that this is the structure? It's quite complicated. We see lots of functional groups that seem to repeat. There's ethers all over the place. It looks like there's lots of alcohol groups, quite a number of alkenes, and moreover, there's stereochemical information, see all those wedges and dashes, for instance, that we would need to work out as well. So if you think about the types of analytical techniques that you've learned about in lab and lecture last semester, you think of things like GC or IR or melting point. And I would argue that none of those will allow you to actually determine the total structure of mitotoxin. And that's a big problem, right? Generally, we want to know what the actual molecular structure of a compound is, especially because maybe we don't really want to make mitotoxin because it's probably going to be a lot more expensive to kill mice this way than with a mousetrap. But maybe we can make adjustments to the structure, so long as we know the structure, to make other compounds that have useful functions for us. So this unit is about a technique that allows us to actually determine structure in a much more reliable way than IR or GC or melting point. And it's going to take advantage of the fact that most organic molecules have lots of hydrogen atoms. So some of them in the structure of mitotoxin that you're seeing are explicitly drawn. You can see all the H's. But you also know that quite a number of the hydrogens in this molecule are implicit, and they basically create a coating all around the outside of the structure. Almost every carbon in this compound has at least one hydrogen attached to it. So maybe if we could measure something about the chemical environments, or essentially what's nearby the hydrogens, if we measure that for all of the hydrogens, maybe we could actually figure out what the structure of mitotoxin is. Right? So this is essentially the crux of NMR. And it turns out that this is a technique that you might have actually thought about before in a different capacity. NMR is exactly the same as MRI, or magnetic resonance imaging. So this is a picture of like a simple looking MRI instrument in a hospital. One of these instruments will typically cost about $4 million to install. That's pretty expensive. NMR looks a little different. So this is a nuclear magnetic resonance instrument at a university, not LMU. We do have an instrument, but it's not these. And so you can see that this looks very simple relative to the MRI, in part because patients aren't going to see this. It doesn't need to look fancy. You also might wonder about the name. So why do we not just call this like molecular MRI, or just call MRI in a hospital NMR, since they are actually the exact same technique? Well, I bet you can figure this out. What word in NMR, or nuclear magnetic resonance, do you think might freak patients out? Exactly. This is the only reason why we have two different terms for this technique, either MRI or NMR. It's that doctors basically hold their patients to a very low standard of critical thinking, which is kind of disappointing. So there's basically 3 questions we want to answer in this video about NMR. What types of physical principles are actually working in an NMR instrument? So maybe stated a different way, like how does NMR work at its most basic level? We'd also like to know what we're actually measuring by NMR. I gave you a kind of a simplified version of that earlier in the video when I mentioned something about measuring things about the local environments of hydrogens. Well, we'll be more specific than that by the end of the video. And then finally, at the end of the video, we'll start to talk about how we can actually take measurements from NMR to learn something about structure. So think about this video as essentially the groundwork or the framework upon which we will build the rest of our understanding of NMR. So to get started, we'll think about the physics. And I want to be clear here that I'm going to show you some equations and I'm going to bring in some concepts from physics too, but you won't necessarily be evaluated on like doing calculations or knowing constants or anything like that. It is important to me, however, that you know that NMR is not a black box. We do have a very detailed understanding about the physics and the basic mechanics of what's happening inside of the instrument. That said, our treatment is going to be a simplification, right? So there's going to be some things here that they're kind of lies, but they're useful lies. NMR physics is quite complicated, and it doesn't serve you any good or me any good to actually go into detail here. So we'll start by thinking about a property of nuclei. It could be a hydrogen nucleus, but it could be a carbon nucleus or something else. These nuclei can have something called spin. And you've encountered this concept of spin before. You've just assigned it to electrons. So when you drew orbital diagrams in Gen Chem 1, you probably drew like arrows that pointed up and down, and you put those over a horizontal line, and the arrows up and down tell you something about spin. You might remember that that's one of your quantum numbers, m sub s. So nuclei have spin also, and we describe this spin with what's called a spin number, which is a vector quantity, so it's the capital S with that little vector sign on the top. And the spin is going to be something other than 0 as long as either the number of neutrons or the number of protons in the nucleus that we're thinking about is odd. Or they could both be odd. Any of those situations will work. So you see a table here for hydrogen nucleus, so 1H, right? There's one proton, no neutrons. So we've got an odd number of protons and we've got a spin number that's not 0, right? That's the only thing I care about here. The spin number cannot be 0. So you can see that there's a few different kinds of nuclei for which this is relevant. An isotope of hydrogen, which we call deuterium, sometimes called D, has a spin number that's not 0. On the other hand, carbon-12, which might be useful for us to think about given this is organic chemistry and there's a lot of carbon atoms involved, that spin number for carbon-12 is actually 0. And then you can see some other nuclei as well, fluorine and phosphorus, for instance. We'll talk a little bit about those in a different video later on in our discussion. So why do we care that the spin number not be 0? Well, because that's the fact is that if a nucleus has a spin number that's not 0, that nucleus also has what's called a magnetic moment, which we denote with this mu. It looks a little bit like a messed up m, again with a vector hat over it because it is a vector quantity. And gamma is what's called a gyromagnetic ratio. So this is a constant for a given nucleus. So for instance, like a hydrogen nucleus has its own gyromagnetic ratio value. A carbon-12 nucleus has a different one. A phosphorus-31 nucleus has a different gyromagnetic ratio. The point is that each nucleus has a constant here. And what I want to focus on is the magnetic moment. We need a magnetic moment that's not 0 for NMR to actually work at all. And we know from this basic equation that if S is 0, the magnetic moment will also need to be 0. So this is why we care about the spin number, right? We need that magnetic moment. Because if we have a magnetic moment, the nucleus will actually interact with a magnetic field, right? This is the crux for how NMR works in a physical sense. We're actually going to interact these nuclei with a magnetic field. And the interactions that happen there, we're going to measure in an indirect way, and that will eventually give us structural information. So let's look at this in a graphical sense. We could imagine all of our nuclei as these red spheres, or circles, I guess, and they have these magnetic moments, which are the red arrows, that are all pointing in different directions. It's random. Please ignore the spinning circular thing. Spin is misleading. It does not mean that these nuclei are literally spinning around like a top or, a car that's been hit and is spinning out of control or anything like that. That doesn't work. So I don't know why we call it spin, but there's no movement involved here. Okay, so this is our picture when our nuclei are just chilling in an environment where there's really no magnetic field. But if we actually take an NMR instrument like this, most of the inside of that giant cylinder contains a big-ass magnet. So that's a technical term. The B for magnetic field here is for big ass. No, I'm just kidding. But there's a really, really powerful magnet in there. In fact, that magnet is so powerful that for the most modern NMRs, you basically could put a frog inside of the NMR and the magnetic field would be so strong that that frog would levitate, which is kind of cool, I think. So what happens to our spin, or our nuclei spins, when we actually put them inside this magnet, where there's a very powerful magnetic field? Well, it turns out that those spin magnetic moments, right, which are the red arrows, those actually will align with the magnetic field that comes from the big-ass magnet. So if we describe the magnetic field from the big-ass magnet as B naught, there's a green arrow on the right side of your screen. We'll say that that's the direction of the magnetic field from our instrument. And you can see that most of the time, or some of the time rather, the magnetic moments of our nuclei point in the same direction. But they also point in a different direction. So if you look at the right-hand image here very closely, you can see that some of them seem to be pointing in the exact opposite direction. And that's true. There's two orientations that are allowed, either with or against the magnetic field. So sometimes it's helpful to visualize this with a video rather than two static images. So I've shamelessly stolen a video from YouTube. So we'll see this video where we have nuclei, which are depicted as these red spheres, and their magnetic moments, which are going to be these white bars. And we'll see what happens when these magnetic moments interact with
the magnetized nuclei tend to align with the external magnetic field, just as a compass needle aligns with the magnetic field of the Earth.
From the magnets itself. So what this looks like is, back in our static image, these two types of alignment, either with, or sometimes called parallel to, the applied field. We call this an alpha state, or anti-parallel to an applied field, which we call a beta state. So beta means you're pointing the opposite direction from the magnetic field of the instrument. Alpha means you're pointed in the same direction. And maybe intuitively, pointing in the exact same direction is a slightly lower potential energy state than pointing directly against it. So we could say the alpha state is a lower energy and the beta state is a higher energy. Another way of talking about this is that the alpha state is slightly more stable than the beta state. We'll be talking a lot about potential energy this semester, and I'm sure that last semester you heard the word stability a lot. But I want to be clear that whenever we're talking about stability, we're talking about relative potential energies. So the lower a potential energy, the more stable something is. So we could also look at this with respect to like potential energy on more of a diagram. So this is showing you two different kinds of situations. On the left-hand side of the plot, where you can see B naught equals 0, we're outside of our magnet, and there's no energy difference at all between the alpha and beta states. In fact, they don't even exist, right? We saw this picture where all those different magnetic moments were pointed in like random directions. But once we apply the magnetic field from like an instrument, we have these two different states, right? There's two possibilities for our magnetic moments to align, either the alpha state with the field or the beta state against it. And so there's this potential energy difference, which is what I was talking about. So most of the rest of the video will be using these kinds of potential energy diagrams. This notion that the alpha state is lower in potential than the beta. And I also want to be clear that what we're talking about are collections of nuclei. So your sample for like IR or GC would not just be a single atom, would it? And that's not going to be true for NMR either. It'll be a collection of millions or more likely billions of molecules. And each of those molecules has nuclei. So we're talking about like collections. So I also want to show you that there's a small potential energy difference between the alpha and beta state. That it's not a zero difference. There is a difference, but it's a very small difference. Right? So that's the difference in potential energy, basically 10 to the negative fifth kilojoules per mole. Teeny, tiny, teeny, tiny. And the alpha and beta states are in equilibrium with one another. Right? You can go back and forth, it turns out. But the equilibrium constant is about 1. So that's what that means is that there's essentially just as many alpha state nuclei as there are beta. Very, very, very slightly more alpha than beta because alpha is very, very, very slightly more stable than beta. Okay, so at this point we've answered our first question for the video. What principles are at work in an NMR instrument? Well, we're basically thinking about the fact that some nuclei have spin. Right, that's our spin number. As long as that's not 0, that nucleus has a magnetic moment. And that if it has a magnetic moment, it will interact with the strong magnet inside of the NMR instrument itself. And basically we'll create these two different states, alpha and beta. So what are we actually going to measure then? Well, it turns out we're going to exploit the fact that there's a difference in alpha and beta states. Maybe we could actually measure this energy difference between the two states. Right? I gave you one number earlier, but let's talk a little bit more about where that number would come from, how we could acquire it experimentally, for instance. So another way of asking this question is how we would measure this energy difference is to think about, well, how could I go from the alpha state to the beta state? Or another way of thinking about this is to undergo what's called spin flip, basically going from one state to the other. So to do that, I'm going to have to put in energy, right? I'm not going to break physics here. The law of conservation of energy still applies. And so I'll need to apply the exact amount of energy that is the difference between alpha and beta. Essentially, I have to pay to get from alpha to beta, and the price is the difference between the potential energies of those two states. So how can I do that? How can I put energy into a system? Well, you can think back to Gen Chem, for instance, and you probably learned about a few ways. You could heat your sample, you could mechanically agitate, stir or shake really fast your sample. But the way that we often will do this is we actually use light or photons. And you learned that there's this relationship between the frequency of the photon and the energy of the photon. So you don't need to remember the equation or anything like that, but remember that a photon is a packet of energy, and that we describe the frequency of the photon to talk about its energy. So we can actually look at now directly, because we can measure photon frequency. In fact, we do this with our sight, for instance. That's how we see color. For the photon that actually is absorbed, for instance, or emitted, depending on which way we go, from alpha to beta or beta to alpha, associated with this gap. So if I know what frequency a photon creates the transition, like for instance is absorbed and the transition happens, then I know how much energy I put in, and I know the difference between alpha and beta. So how does this actually work in practice inside of an NMR instrument? Well, we'll look at this in a few different steps. We'll start with a situation where we've got our sample, we've put it inside the NMR, we've got lots and lots and lots of nuclei, lots of different hydrogen atoms, for instance. We know that, at least initially, we have alpha states and beta states, and we've got very slightly more alpha than beta. So I'm only showing 7 dots for the nuclei here. It would realistically be billions and billions of dots, but I don't want to draw that. So we're going to use these dots as kind of a hypothetical, right? So this is kind of the equilibrium state. A little bit of alpha, a little bit of beta, slightly more alpha than beta. So what we'll do is actually play music to your NMR sample. We're going to play lots of different frequencies of photons. We're going to bombard the sample with like every possible photon frequency we can think of within a region. Because these energy differences between alpha and beta are so small, we need very, very low frequency photons. And so we're really talking about like radio waves. So if you want to make a silly analogy here, we're playing a radio station, or actually every radio station, to the NMR sample. And what that does, because we're basically providing every possible frequency, no matter what the difference between alpha and beta is, we create these transitions where the alpha state particles, or spins, get excited and go into the beta state. So that gives us a situation that looks more like this on the far right, where almost all of the spin states are beta. Only a very small number are still alpha. And we call this a population inversion, mostly because we're no longer at equilibrium. We're at a far less stable state overall than we would be if we had most of those alpha spins back. So these population inversions we can create by putting energy in. And that's what we're doing by playing all these different radio stations or playing all these different radio waves. This is very similar to how a laser works. And we know that this, because it's not at equilibrium, we're actually at a higher energy state than equilibrium would be, that there'll be a spontaneous change, or we go backwards, where all of these beta states, some of them will relax back down to the alpha state. And in doing so, they'll have to release energy. But now they're only going to release photons with a frequency that is the actual energy difference between the beta and the alpha state. So to think about it another way, what we're going to do is play like every possible radio station to the sample, then we're going to stop, and then we're going to start listening. And we'll get a few radio stations back. right? So there'll just be a few possible beta to alpha transitions that happen, and we get these what are called resonance or resonant frequencies back. So we're measuring photons, right? And in particular, we're measuring resonance frequencies from the photons that are happening from relaxation. So our last question is, well, a resonance frequency seems pretty esoteric. Like, how does that tell me the structure of mitotoxin? Good question. And this is the one that's probably the hardest to answer. And to be honest, we won't have a complete answer until the very end of this unit of the class. But we'll start the discussion today. So when we're talking about this model so far, we've basically been implying that there's really only one kind of alpha state and one kind of beta state. And the implication here is that every hydrogen atom in a molecule would give you the exact same resonance frequency or the exact same signal. Well, that's not helpful. I don't necessarily need to know like how many hydrogens there are. I need to know something about how each of them differ from one another. That's what gives me the structural information. So the insight that we have is that, well, resonance frequency appears to be dictated by a couple of things. The gyromagnetic ratio, so that's the constant for the nucleus. That's not helpful in and of itself because every hydrogen atom has the same gyromagnetic ratio, but also the strength of the magnetic field. So if I make the instrument stronger, like if I make the big ass magnet even more bigger asserer, then this energy difference gets bigger. So another way of thinking about that is that our resonance frequency is like proportional to the strength of the magnetic field. So you can look at an example here where we're basically changing the strength of the magnetic field on the x-axis, and depending on how far to the right we are, we can see that the alpha and beta states are getting further and further apart in potential energy. And it's this proportionality that's going to end up giving rise to a way to differentiate hydrogen atoms, but it comes from an indirect source. And that's what we call Lenz's law. So this is an idea that's covered in most Physics 2 classes. Don't worry if you haven't taken that class before, or if you don't remember Lenz's law. The idea with bringing it up in this video is to give you a basic grounding and a physical understanding for NMR. You don't need to do any calculations. You don't need to know the equations associated with Lenz's law, just the general concept that we'll discuss here. So what we can think about is that if electrons are moving inside of an external magnetic field, those electrons create their own what's called induced magnetic field. So the magnetic field they're creating, the electrons are creating, is induced because of this movement. And that induced magnetic field, it opposes the external field, so it basically pushes back against it. So we can actually see this effect in an interesting example. So no nuclei here, this is straight physics. And so we can see this in action with a copper pipe. And this is a video that's been made by MIT, so thanks, dorks. The idea here is that there's a copper pipe. And that's not me. But this very handsome gentleman has an iron ball. And when we drop it through the pipe, it falls through. Wow, it's very surprising. Moves pretty quickly. Wait for it. Ooh, spherical magnet. Okay, so this is like a magnetized ball. Wait, where'd it go? What? What? Oh, now it's out. Okay, so this seems like magic. This is concerning. Oh, it happened. Okay, so it's reliable, repeatable. Interesting. So the difference in this example and how we're going to apply this with NMR is that we don't need to create our current because we're talking about electrons that do move, and that means that we already have this moving current, right? But otherwise, it's the exact same principle, right? What we're seeing here, this witchcraft, is that induced magnetic field essentially holding up the magnet as it falls through. So that's essentially Lenz's law. So let's apply this to nuclei. If we have electrons that are moving near a nucleus, like let's say electrons that are near the nucleus of a hydrogen atom, those electrons, because they're moving inside of our instrument, are going to create their own induced magnetic field, and that induced magnetic field will oppose the big-ass magnet, will oppose the external field. So what that means is that the nucleus itself will actually experience what we can call like an effective magnetic field, or B sub-effective, or BEF. And that's like literally the sum of the external field and the induced field. So because we know the induced field opposes the external field, we're going to subtract. And that means the effective magnetic field of a nucleus will always be reduced relative to the instrument strength by any electrons that are nearby. We call this shielding, or if we feel like being real fancy, we could call it diamagnetic shielding. So we have this introduction of what electrons do now. So again, back to our potential energy diagram, if all we had was an external magnetic field, no electrons, no Lenz's law, all hydrogens would have the exact same resonant frequency, right? At least within a particular instrument, B naught will be the same, right, for the instrument every time, and the gyromagnetic ratio is the same. So NMR would be useless if we had no electrons. But if we have electrons, we actually change where we are on this plot, right? Because remember, we're not plotting on the x-axis the magnetic field from the instrument. We're plotting the magnetic field that the nucleus experiences, or BEF. And we know that that's a composite of both the external magnet and the induced magnetic field from the electrons. So how is this helpful? Well, BEF is going to be directly proportional to the resonance frequency. BEF is essentially going to dictate, along with the constant, the difference in energy between alpha and beta. Another way of saying that is that the effective magnetic field will dictate the resonance frequency for spin flipping. So how will that help us? Well, we're trying to decide whether the impact of induced magnetic fields from nearby electrons can help us actually tell one hydrogen from another, or differentiate them. And I think we could actually do this together, or rather you could think through it. So let's say we had two different hydrogens in a molecule, and they each had different amounts of electron density nearby. So we have a few different variables. We've got B naught, we've got Bi, we've got BEF, for instance. Which of those variables will be different between these two hydrogens? Or another way of saying that is, like, where will our differentiation come in with respect to B naught, Bi, and BEF? So take a minute, pause your video. I'd like for you to think this through. Like, which of our variables do you think is impacted by these different amounts of electron density? All right, so you've had a chance to think this through. And it turns out that two of the three variables change. So the induced magnetic fields, so we could talk about like B sub I sub 1 for our first hydrogen nucleus and B sub I sub 2 for our second hydrogen. Those can change, right? So if we have more electron density, then we're going to have more induced magnetic field, right? So the electrons create the induced field. So if there's like more electrons, we get more field. And because BEF is essentially a function of the induced magnetic field, then we know that BEF will change. So we'll have two different B effectives, right? BEF sub 1 and BEF sub 2, which we'll call them. So if we look at our plot here, we have like now two different situations. We're at two different places on our split between alpha and beta in an energy sense, right? So if we've got like more shielding, like B sub I sub 1, for instance, then we're further to the left on our plot, and our B effective is smaller, right? So we're further to the left on the x-axis. And if we've got less shielding, maybe like less electron density from B sub I sub 2, for instance, then we're further to the right on the x-axis, and our B effective is going to be a larger number. So we can see that depending on where we are on the x-axis, what our B effective is, we actually have like two different resonance frequencies, right? The difference in energy between the alpha and beta state is going to be driving what this frequency is. So I basically can actually tell the difference between my two hydrogen atoms by knowing something about how much electron density is nearby, which is a structural characteristic, right? So basically, the more electron density I have, the more shielded I am, and my resonance frequency changes from a hydrogen that is going to have less electron density and is less shielded. So what we'll get is, if we, let's say we really only had two different hydrogen atoms in a molecule, we'll get like two different photons back, two different kinds of photons with different frequencies, and I can listen to those or hear those independently. So our resonance frequency here is what we're going to be actually using to gain structural information, right? Our resonance frequency is going to indicate something about the relative amount of electron density. And then we can take that information about electron density and we can correlate it with structural features, right? So maybe a functional group nearby makes hydrogen electron rich or electron poor, for instance, and NMR will essentially show us that. So we've answered three different questions in this video. One is really like what physical principles are applicable for NMR, and that's essentially this concept of nuclear spin, right? If we've got a spin number that's not zero, we'll be able to have a magnetic moment for the nucleus, and that magnetic moment will align in an external magnetic field, which is like what our instrument provides. What we actually measure with NMR are resonance frequencies of photons that come from spin relaxations, from spins going from the beta state to the alpha state. Right? That frequency of the photon that comes out during that transition is directly equal to the energy difference between that beta and alpha state. And when we actually then go to actually get structural information from those measurements, what we can say is that, well, the difference in energy between that alpha and beta state is going to be a function in part of the amount of electron density that's near the hydrogen, right? So those are the three things that we learned in this video. And the next video, we'll be taking a step toward looking at actual NMR spectra and starting to do the work of really correlating electron density to the structural features and how we actually assess those things in the spectrum itself. It turns out it doesn't look anything like the potential energy diagrams that we've done today.